So now I will give the full definition of our main object, we can say, finitely cyclic operator. And first let me recall what was a cyclic operator. So we consider now, this is quite an abstract situation, but of course we will be soon in the Hilbert space. But generally speaking, when A is a linear operator in a normed space X, so A is cyclic if and only if, and I will introduce here notion orbit for the operator A of a vector phi. Moment. First, if and only if there exists a cyclic vector for A. And what does it mean that it's cyclic? It's cyclic when its orbit is dense. Yes, what does it mean? Orbit, everyone can guess that the orbit is just the set of all powers of n on phi where n is from the natural numbers, including also zero number. And so phi is cyclic for A if and only if. First condition is that those phi should belong to the domain of so-called A infinity, we need that it has sense, yes, for any n. So this and the orbit of phi with respect to R A is dense. So this is the cyclic situation. Yes, and the last time I told you that finitely cyclic is similar, but
it's capital S.
What is capital what?
X.
I consider this is this is the general situation. Yes, but next this is just for the general definition, because the notion has sense in any normed space, even it's not necessary to be the Banach space. Yes, this should be it is enough to be the topological space. Yes, this is just the notion of closure should have sense, and it's not important. But of course we will do this everything in the Hilbert space. Okay, so now finitely cyclic, and so similarly A is finitely cyclic. If and only if there exists natural D and a system, I will write this is phi with an arrow. This is just an element of x to the power d. So this is a system of d vectors. Yes, the system of d vectors. So just we can say d elements, but with an ordered system in the sense that they are ordered. Yes. So this is equal to phi1, phi2, and so on to phi d, yes. And each one is just an element of X. So there exists D and a system phi in XD, which is cyclic. I will call this cyclic. This is cyclic for A, where what does it mean that this is cyclic? Phi arrow is cyclic if and only if, and similarly we'll define the orbit. So first the definition of the orbit with respect to A of phi with the arrow is just the set of all A to the power n phi j, where n as before is from the natural numbers and 0, and j is equal from 1 to d. So just we make the same but for all the elements of the system. And what we need is that this orbit is dense. Yes? That's true. It's not, of course, it will be hypercyclic. It will be called hypercyclic, and it's not for us. Thank you very much. Of course, you want here the linear space first and then closure. Thank you very much. If and only if the linear space obtained from the orbit, so we can just say it's linearly dense, yes, instead of writing this closure. It's linearly dense, so the linear span of orbit is dense, of course, yes. And without this linear, it is hypercyclicity is very special condition, almost impossible for self-adjoint situation in Hilbert space. But also very important, but for instance for house studies. Okay, so this is just the definition. Okay, observe that we do not assume, for instance, that this system is linearly independent or something like that. We just call this system, we just call this cyclic, but it can have more elements that we just can repeat some of them, and this is not important here. Okay. So this is the definition. Yes. And now, maybe the example. I told you that for the cyclic situation, scalar Jacobi operators are the typical operators which are cyclic. And here we can consider block Jacobi matrices. So assume that we have block Jacobi matrix first. When we have block Jacobi matrix, what is this? This is formal, we can say formal matrix, which is half infinite. So we use numeration, for instance, from 0, 1, and so on, 0, 1, 2, and so on. So we we just number the columns and rows, and in each square on the diagonal we have a D by D matrix. Let us denote it by B. This is B0, B1, B2, and so on. And we assume that so B, J, and A, J, they are D by D square matrices, complex matrices. Those B are self-adjoint. And here we can take A1, yes, no, A0. I forgot the numeration. Okay, it's not important here. We can write like you want. Let it be A0, A1. And here we can take any matrix, but the adjoint should be here. This is A adjoint, and so on. But we assume that each Aj is invertible. So the determinant is not non-zero. So this is the formal operator, and then having this, we can consider many operators on several domains, and typically we can consider first we should have the Hilbert space. So our Hilbert space is L2 on N0 CD. Yes, matrices were D by D. So what does it mean? These are sequences with terms in CD. Yes, numbered by numbers 0, 1, and so on. So let me write this like A2D, just simply. And for instance, we can take first the minimal operator J, which has the domain just equal to finite sequences. Finite, it means that starting from a number they are 0. Yes? D2, just D fin, I will write like this. So this is a small domain but dense, and then better let us define this like J null, okay, J0, and J minima is just the closure of this, okay? This is one possibility. Sometimes it is self-adjoint, sometimes it's not. There is a large theory about this self-adjoint. And also we can take the maxima. So I will say only what is the difference. For J maxima, we take, in some sense, the biggest domain in L2 for which the formal formula for the operator gives an element in the space. Yes. So this is another operator which is related to this, and the situation is like this, that usually there are conditions for which of course this operator is always symmetric, just even this J0, and it can have some self-adjoint extensions. But even for this operator, in some sense, this J nor is the smallest operator which is interesting. It's easy to check that this J0 is finitely cyclic. So, what is the cyclic system? We can take the following system. Where phi j is a sequence like this. On the place number j, on the place number, on the first place, we take just aj. This is number 0, not the first, but number 0. Yes, the term 0 of the sequence is aj. Aj is the sequence is an element, a vector from CD, which has a form like this. On the place j, it has 1, and the rest is 0. Yes. And here we have 0. So taking such a system, it's quite easy to check using the fact that the determinant is non-zero, that when we take this linear span, we will just obtain the space of finite sequences, which is dense. It's quite a simple computation to check this. So this is an example, typical example of an operator which can be self-adjoint sometimes, and it is cyclic. And our theory will be not cyclic, but finitely cyclic, yes? This is finitely cyclic. But the system is called cyclic. But operator is finitely cyclic. Okay. So our theory works for instance, would work for instance, for all block Jacobi matrices which are self-adjoint. In the sense that not that it's a self-adjoint extension of such an operator. Of course, when this is finitely cyclic, then also the same system is good cyclic system for an extension. Yes. Okay. So now we are trying to formulate a theorem, but we should have some good notions. And I would like to recall you that in the situation with cyclic operator, our, we can say, main object, which was very important, was the measure. Yes, the measure, which, in some sense, coded all the information about the operator. It was the spectral measure for the operator and fixed cyclic vector. Yes, it was something like this. And now we'll define something similar, but it would be for a fixed for a fixed cyclic vector, and for an operator, of course, and its fixed cyclic vector, a vector system of vectors, we define the matrix measure. Matrix measure, which will be an analog of something like this. But now it should be not the measure, but the matrix measure. So, we again assume that A is self-adjoint in a Hilbert space H, and just to define the matrix measure, we do not need even the cyclicity, we just need a system. Yes, we need a system, so we assume that phi L is just a system of D vectors from the space. And we will define, so first of all, we know that when it's self-adjoint, so E of A is the spectral measure for the operator A, so for each Borel set on R, we have the projection, you can write projection orthogonal on H. This is a set of all orthogonal projections on H. And having this, we will now define something which I will denote like this, similarly like for the spectral measure for cyclic operator, but with the arrow now. So this would be from Borel subset of R into the matrices, D by D matrices, complex matrices, and the definition is as follows. For any Borel set omega, what we take? We will take the matrix. So we will just write here what is the term in the row number I and column number J. So for E, I, J from 1 to D, yes, I will take here the scalar product, just the scalar product. So we take we take the operator, our spectral projection for this operator of the omega, and we will use here the terms of this system phi. And this is important that we take phi j here and phi a here. We should not change this. Yes, this is important here. Okay, so this is our definition. This is the definition of something which belongs here, yes? But then it's easy to check, it's simple calculation. Let us write this is fine. But this is a matrix measure. And this is just easy calculation. This is non-negative, and this is, of course, this is This is countably additive, yes, because the spectral measure is weakly countably additive. So it is obvious, but the only thing which should be checked that this is not negative, but this is, of course, it follows from this that spectral projections are non-negative in the Hilbert space. So it's easy. We just, in some sense, we cut, we take a cut, we act only on some vectors. And it's not important that they can be linearly dependent, it doesn't change anything. Okay, so we have a matrix measure, and it's an analog of our spectral measure for a fixed one vector. And you will see that this is the crucial matrix measure for us. And now the name. We will call this, the name of this measure is the spectral matrix measure for A and the system phi arrow. So for each self-adjoint operator and each system we have something like that. We have a well-defined spectral matrix measure. Now you would like to start to formulate some results which would allow us to formulate the main theorem and to prove it. So this is important maybe to recall one subspace, one linear subspace of the space L2 of M. It's something what I told at the last moment on Monday, so I will repeat this. We will use this subspace, which is sometimes equal to the whole space. For instance, when D is equal to 1, it's the same just, but generally it's not. So this is L2 sigma, and okay, I will write this for general matrix measure M, but we will use this for such a matrix measure like here. So what is this? This is the space of all classes just belonging to L2 of M, such that F belongs to the calligraphic L sigma 2 of M, and this calligraphic one is the calligraphic L2 of M is the set of all such functions F from omega to CD which are measurable, that when we take any term, J term of this, for any J from 1 to D, Fj belongs to the space L2 for the measure Mjj. This is just a measure from the diagonal of the matrix, yes, which is the measure. So for each J, it should belong to such a space. L2, I am sorry, of course, yes, it is this, yes? And let me recall that in this situation, when we have two elements of this, when we have f and j from this, then there is an alternative way of to compute the scalar product. So when I take class of f and class of g, I can compute this scalar product without using the densities, the matrix density of the matrix measure. Sorry, not matrix density, but trace density of the matrix measure. And the formula is like this. We just take the sum over all a and j from 1 to d of integrals on omega, and there we should be careful with the order f j I d m I j, yes, something like this, and it can be proved that it has sense. Each such integral has sense. It's by this assumption. It's not trivial, but it's not very difficult. Yes. So, and this is a convenient way sometimes to compute the scalar products. Okay. So now, and maybe it's good to say that maybe you remember the classical, maybe not the classical, but maybe you know the books of Rudin on, I think it's not the functional analysis, but it's a real complex analysis, and there is a Rudin's way of, for instance, of proving that Fourier transform is a unitary transform of the L2 space. And the proof of Rudin is based on a Schwarz class of functions. And it's very elegant proof. And in this proof, first it's proved that on Schwarz functions, on the class of Schwarz functions, the Fourier transform is an isometry, which is invertible isometry, which transforms Schwarz function onto Schwarz functions. So, in some sense, in our later proof, those subspace will play the similar role as the Schwarz functions in the Rudin's proof. It's convenient from some, I can say, algebraic point of view in our proof. Okay. So now, theorem. Maybe here. So I will not use still the property that our system of vector is cyclic, because now it's not important. It will be important soon, but not now. Theorem. So A is self-adjoint in H. Phi arrow is just a system of the dimension d, where d is natural, and let us denote for short that M is just the matrix, the spectral matrix measure for A and phi arrow, okay? So this is equal to E A phi arrow. Then point I, first point, for any f from our calligraphic L2 sigma of M and J from 1 to D, phi J belongs to the domain of f J of A. Yes, we take f from this space and we take its jth term, so this is a scalar function. We take this scalar function of A and our assertion is that phi j belongs to the domain of it. Yes, it's number one. Number two, the linear transformation W tilde from L2 sigma of M into H given by W tilde on F equal to the sum from 1 to D, and what we sum? We just sum values of this operator on this. Fj of A onto phi j for any f belonging to L2 sigma of M. So this linear transformation satisfies the condition for any f from our 2 sigma space. The norm in H of WF is equal to the, we can say, just the norm of the appropriate element in our space A2. So, in other words, our assertion is that we have an isometry on this subspace.
Is phi a cyclic system?
Is
Phi. Is phi the cyclic system?
No, I don't assume. Now it's any. Now I do not need this. In this theorem it's not important. Any. Okay? And soon I will, to get more, I will need the cyclicity, but now it's just a system. It can be even a zero system. But nothing important will happen here. Just a trivial transformation. No, well, maybe not completely trivial. I don't know. But it's not important. Okay, the point 3. The transformation W without tilde from L to sigma, but capital L to sigma M into H given by W on the class F just like this, yes, for F belonging to L2 sigma of M is properly defined. Which means, what does it mean? It means that W of F is 0 for such F which belongs to the intersection of L2 sigma of M with the 0 layer. Yes. And it is a linear isometry into H, not onto, yes, it will be onto when we assume the cyclicity, we can guess, yes, but now it's into H. So, I will give almost the whole proof, but without proving some lemma. I will write some abstract lemmas. And I will show how we can use this. So, I will write here two lemmas on complex spectral measures. So, lemma 1. Let A be self-adjoint in H. Let A be equal to just A equal to A, E equal to EA, yes, the spectral measure for A. And assume that we have the Borel function on R, Borel function. It means it's measurable with respect to the Borel sigma algebra on R, yes. And assume that X belongs to H and Z belongs to the domain of the function f of A. We consider such two vectors. Yes, one is from the domain of f of A, the second one, and this is just any vector from H. Then f conjugated belongs to the space L1 with respect to the spectral measure AXZ, and AXFA of Z, when we take such a pair of vectors and we want to compute the spectral measure with respect to such two vectors, it is, you can say, it has the density with respect to the measure to this measure, and this, the density is this. So this is the lemma, which is not very difficult to obtain, which is well known, for instance, from Rudin's functional analysis book, but only in the case when f is bounded. And this is true for any, just for any measurable Borel functions. So this is lemma 1, and from this lemma 2, from this lemma 1, we can obtain something a little bit more sophisticated when we take two functions on x and on z. So the second lemma. So the beginning is as above. So lemma 2. So this is the same. So we have A in H and the spectral measure, but we take two functions, two Borel functions, f and g are two Borel functions. And now x belongs to the domain of f of A, and y belongs to the domain of j of A. Then f j conjugated belongs to A1 with respect to Ax y, and when we take here the spectral measure for f a of x and g a of y, we will obtain the measure with the density f times g conjugated with respect to this. A od from f of a on x and j of a of y is just equal to f g conjugated d a of x y. Let me recall that this means this is a complex measure. So what does it mean, this symbol? It means that it belongs to the space L1 with respect to the variation measure of this measure. Yes. So it makes sense, everything. Okay. So having this lemma.
At some moment we should make the second break.
Okay, we can make it. Maybe. Okay, we can make it now. Only I would like to say that after proving this, it's very easy to get this. It's just we must use this twice. Use this, yes, and we obtain this. So this is easy, and this is also not very difficult. So I will not prove this, but I will show after the break. I will show main calculation from the proof of this, which is based on this lemma too. Yes. So now let's make the break.